Okay, it looks like it's official, folks. We can begin. So we finish off section 5.1. Really, our major takeaway at 5.1 is getting fluid with radian measure and knowing where all the important angles end up in radian measure. So the first diagram in this additional file here, it is an optional file, but it's helpful, I'd say. This one relates the angles with the degree measurements. The angles in radian measurement, I'd say, are the more important takeaway from here. And when we go to the next diagram, this is giving you the outputs of sine and cosine for all of these common angles, like pi over 3, or maybe pi, 7 pi over 6. The takeaway for 5.2 is sine and cosine are defined on the unit circle. Cosine is going to be the first coordinate. Sine is going to be the second coordinate. So that's our major takeaway when we go into section 5.2. So 5.1, all about the domain of those trigonometric functions, and that common angles is a very important document. And now 5.2, we finally define the unit circle sine and cosine functions. Actually, let me open it this way. Here are the notes, so it's how we'll work on it. But one other reminder, since we finished section 5.1 on last class meeting, the due date is going to be this next upcoming Tuesday. So these due dates are really and truly in flux. This one says it's going to be due Thursday, January 25th, but that's if and only if we finish it today. I think we probably won't. I don't want to try to race through that document. It's extremely important. We're firstly defining the functions. So always think of these due dates as really being truly in flux. It only becomes official when these notes are completed, and then this is always going to be a 1 week turnaround after we completed those notes for the due date. Any questions about that at the moment? Okay, well, let's jump down into section 5.2 next. So here's how it goes. We're going to define the trigonometric functions, but let me make sure not to ignore Zoom and get the participation window in there. Let me see if I can redo these windows just slightly better. That ought to work for us. Okay. So here, to start it out, it says we're going to let t be an angle in standard position. So it's going to be measured off the positive x-axis. And let a point, pxy, be a point where the terminal side of t intersects the unit circle. So that's our first part of the definition, and let's walk through it. We need an illustration to go with this immediately. And let's start with this part, the unit circle. To draw the unit circle, the trick here is try to just go really fast, just sort of whip it out. And well, that one's not great, but I wouldn't be too picky either. If it looks slightly oblong, I wouldn't worry about it. Let's try one more time. Well, I'll settle with that one. That's our unit circle. Then throw some crosshairs on it. When it says t is an angle in standard position, that means we're measured off this positive x-axis like we said. Pxy will be the point where the terminal side intersects that unit circle. So we're starting here. Let's rotate counterclockwise. That's a positive angle. And we can terminate wherever we want. This is just an illustration, so it's going to be arbitrary. We'll terminate it, say, here. So there's the terminal side of the angle t. And once we terminated on the unit circle, we ended up at a point pxy. So there it is. I'll just call it xy for short. Now finally, once we get there, here are the definitions of the trigonometric functions. Cosine at this rotation t is the first coordinate x itself. So if you were to project down, that position is cosine of t. It's a number that can be as minimal as -1 and as maximal as +1, because as t rotates, it's always that first coordinate, and you're always picking off this right value on the x-axis. For sine of t, you just do the opposite thing. Right in this location is sine t, the second coordinate. Then that also tells us the maximum sine we'll ever take is a +1 up here. The minimum we'll ever take is a -1 down here. So there we have it, folks. That's our definition of the trigonometric functions, cosine and sine. We have 4 more to go, but these are the major ones we would want to define first to get all 6. Any questions at all, folks, with our unit circle diagram and the sine cosine defined? Okay, down below, I just have some really fast problems to practice. And by the way, when you see the homework set, it might look like Mike just lost it. He's pissed at something. There's a lot of problems, but these are just really, really fast problems. So if you see a lot of them, they're probably more like what you see down here. We're doing a lot of problems, but they're very, very fast. I'll try to keep the assignments about the same in length to the best of my ability. So we're going to evaluate these things here. First thing we want to do is find the value of cosine of pi. Some folks might have this down immediately. If you do, feel free to shout it out. But first, Alex says, could you pause on the circle real quick? So right here, Alex. Yep, you betcha. So to calculate cosine pi or sine pi, really the first thing you have to know is, well, where is pi on the unit circle? Anyone recall where that would be? Say half a circle. I think that's a great way to specify it. It would be way out here. So really, we're going to start by maybe doing this. Let's draw a really fast unit circle right down here. The angle in question is pi. It emerges right in this location. And once you're here, because this is a unit circle, the equation is x squared plus y squared equals 1. That means you can say go to this coordinate and get -1, 0. Let's put it down here. -1, 0 is the coordinates relative to pi. That does it for us, folks. That says cosine. Anyone see which one it will be? Is it -1 or is it 0? Good call. Cosine is the first coordinate. It must be -1. Sine is the second coordinate. It must be 0. So that's the name of the game, folks. We need to know exactly where our angles are so that we can know which coordinate to pull, and then that evaluates the trigonometric functions. These are just a one-step evaluation. But let's try it again. Sine at pi over 2, well, we need to know where pi over 2 is. Anyone recall what position that would be on the unit circle? Exactly, it's 1/4 turn, 90 degrees, so way up here is our pi over 2. And now that we're doing this, the moment you put down a unit circle, it might not be a bad idea to put down 0. We're going to be dealing with cosine 0, rotated 90 degrees for pi over 2. I'll help with these. Rotate again for pi. And then down below here is 3 pi over 2. In case 3 pi over 2 comes up. Doesn't look like it made the mention anywhere. So now let's try out a few more. How about for folks over in Zoom? Has anyone spotted what the value for, say, sine pi over 2 should come out as?
Is it 1?
Yep, exactly. This one should come out exactly as 1. Good call. That's because right here at pi over 2, the coordinates right here go 0, 1. Sine is the second coordinate. Cosine is the first coordinate, so cosine at pi over 2 automatically a 0. Kind of our goal with this is we're using this diagram as support. And this is pretty typical when you're learning trigonometry, drawing lots of unit circles, drawing the angles on them. But once you get really fluent with trigonometry, the goal is to just see those and know sine pi over 2 is 1, cosine pi over 2 is 0, without drawing anything. Maybe you'll look at a mental picture. But for the moment, we're practicing, so we'll draw all these out. I encourage you to do the same in the homework. Not because it's required, but in the homework, if you get in the habit of doing this, you're building a mental picture in your head every single time, say, cosine 0 comes up. It's going to make everything you do with trigonometry much faster if you start off by sketching these out while you're learning. So let's go and do this again. We're talking about cosine 0, sine 0 on this next one. So the rotation is here. No rotation. The initial side overlaps with the terminal side. Exactly. Coordinates go 1, 0. So cosine 0 is 1. Sine 0 is 0, just as you said. So those are some interesting values. Next, This one's a bit rude, so we'll do a new diagram for this one, but it's really not too bad. Let's go here. Here's our unit circle. And we know pi over 2 is up here. We start the initial side. We rotated this much, quarter turn or 90 degrees. But here for pi over 2, we have to rotate in, oh, I killed my cursor. We have to rotate in the clockwise direction because of the negative sign. So here's 1/4 turn, negative pi over 2. And that's not anything new or interesting. It's the same coordinates right here at 3 pi over 2. So there's a lot of ways to describe every one of these positions. Infinitely many different ways you can describe it. That's another thing that makes trigonometry a little bit tough. Sine at negative pi over 2, cosine negative pi over 2 is exactly the same as sine 3 pi over 2, cosine 3 pi over 2, because the coordinates right here go, oh, let me try again. Control Z that out, Control Z that out of there. It goes 0, -1 here, and still 0, -1 here. So back to sine. Sine at negative pi over 2 will be the second coordinate of -1. Cosine at negative pi over 2 will be the first coordinate right at 0. So that's what evaluations look like with sine and cosine. But the thing that's tricky about this is there was really just 4 angles where you can do these extremely rapidly without too much preparation. They are the angles 0, pi over 2, pi, and 3 pi over 2. Which trig function would return a pi? You'd have to use an inverse trig function to get your pi for that one. And I'd have to think about that. I think a cosine inverse of -1, I'll have to give it to you. But other questions so far? Okay, so this is evaluating sine and cosine with nice angles, like pi, pi over 2, 0, maybe 2 pi. If we try to make it tricky, we're still getting to these nice angles. But our end objective is we need to know sine and cosine for all of these angles in radian measurement. So we definitely have a lot of work to do. But before we do any of that, let's give this problem right down here a try. Example 2. Example 2 says, let Pxy denote a point where the terminal side of theta meets the unit circle. P is going to be in quadrant 3. The second coordinate is -5/13. And we need to calculate sine theta, cosine theta. Really confusing question, just the way it was even stated. And the thing you'd want to do first is the Pythagorean identity. This is the major tool that's going to help us solve example 2. Let's put a little border there. And let's derive that identity. I put it in bold and I highlighted it because this identity, I would say, I'm not sure how to emphasize it. Let's say the importance of this identity, and identity means the equation is true for any value of t whatsoever. That's what we mean by saying it's an identity, always true. So the importance of this identity is gargantuan. It doesn't matter if you're in a different class, say differential equations or even linear algebra, surprisingly, calculus class, an engineering class. If this comes up, we're assumed to know what to do with it. Oh, for complex. You know, that's a great question. I'd have to come back to you on that one. Let me put down a quick note. Pythagorean over complex numbers. That's a great question. I'd have to take a look into that. If I were to give you my gut guess on that, I would say it's probably true, but I would have to absolutely take a look. Complex numbers do wild things. Other questions at the moment? Sorry, say again. How do you read this right here? You would say sine squared of t plus cosine squared of t equals 1. You are, yes. No parentheses at all on this one. It's kind of weird, absolutely. And so what's strange about these functions is I like to put parentheses on mine. That's completely optional. It looks like I didn't even put it on sine t. More often than not, there's no parentheses around your sign. So when you get really fluent with these kinds of functions, people drop them. But when you're learning them, it's a good idea to put parentheses around them. So the identities typically stated in this kind of way, definitely weird to look at. So thanks for mentioning those issues there. But other questions about it so far? Okay, maybe the most important question is, if this thing is so important, we should know why it's true in the first place, right? So let's derive this thing. We'll never do a derivation that's like a terrible slog, but this one's an important one. And a derivation goes like this. It's said for any angle t. So let's just draw an arbitrary one on the unit circle where our trig functions are defined. It didn't have to be a positive angle. We can make it go like this. So here's the angle t. So we've got a negative rotation. We get two values, x and y, in that coordinate right there. Now, next thought is, this circle has an equation. Anyone recall what the equation would be for the unit circle? Exactly. So that's the equation of this thing, the unit circle. But once you write out that much, we have other information that we just looked over. For example, the coordinates x and y are the trig functions. For x, for example, was that sine or is that one cosine? Anyone recall? Good call. Yes, first coordinate is cosine. So when you see that x there, that is cosine. And you see this x here, you're in the same scope, all the variables being the same thing. That's cosine squared living right in that spot. So we'll put it the power 2 here, and here is cosine of t. It's being squared, and then we'll add to it. Here's where y was. It's being squared, but we blew it up with parentheses. This y here is sine of t. So we have cosine t squared, sine of t squared equals 1. Again, all of that is just a consequence. Our function is defined on an object through that equation. So immediately substitute in cosine and sine, and you get this statement out. Now, like what Michael was mentioning earlier, trigonometric functions have weird issues with notation that we have to get used to in this class. First of all, the power is not in a normal spot at all. And second of all, in function notation, I think it's a good idea to keep parentheses around your t when you're learning trigonometry, but it's a stylistic choice as it turns out. In trigonometry, we don't always put a parentheses around our inputs for these functions. Next thing is, a power 2 here is extremely common because this identity is used a lot. So people came up with a new device. This power 2 could be rewritten by saying the cosine function squared with the input of t. So cosine squared of t plus the sine function, this one is also being squared with the input of t. So sine squared of t equals 1. So typically, I like to write out like this. I'm a fan of function notation, so I like to put my input around with parentheses. But we also have to get used to seeing it this way, because in your book, in your homework problems, and just about every other course, it's probably written this way. A lot to get used to out of nowhere. Well, other questions so far, folks, with our Pythagorean identity?
So for this one, like we just have to remember that sine squared t plus cos squared t is equal to 1, right? Not all of this, because it's making me like even more confused if I see all. Like I know what
Yes.
you say, but like,
Equation.
the takeaway is only that one. Yes.
Or you're saying this down here?
Yep.
Yeah, you could treat this as your takeaway,
Mm-hmm.
and you're in really great shape. Absolutely.
Okay. Okay.
Question over here. Sorry. Exactly. The order of operations is really this right here. No matter if it's written this way or this way, you do cosine of the value t, square the result. Absolutely. So order of operations is weird on this kind of thing for sure. Other questions about that? Okay. Well, we've got a brand new identity. I claim its importance is gargantuan. And we'll be the judge of that, not just because of this notes, but for everything we do throughout the course. But we promised that we needed that identity to solve example 2. So now let's make it work for us. Let's scroll down to this spot here where our derivation was. Now start reading through these instructions. This could be a typical homework problem or even an exam problem. And part of our goal is to just take this information and write it out in a format we can really work with, that we can visualize. Let's start with this sentence. Pxy, that's just a point with coordinates xy, is the terminal side of an angle theta in standard position in the unit circle. So from that highlighted sentence, we could draw out this. Here's the unit circle. Not the best unit circle ever, but that's okay. Pxy terminates in quadrant 3. So here's quadrant 1, quadrant 2, quadrant 3. We won't put an angle anywhere around here, but we have one extra bit of information. It doesn't just terminate in quadrant 3. The second coordinate is -5/13. So I'm going to try to plot that. Sorry, say again? Not too sure. That one's going to be a nasty repeating decimal. But right around here, we have -5/13. So that's the second coordinate of an angle. Go right here and project to the left here, where it terminated in quadrant 3. So here's finally our angle. It was an angle theta, so I'll write it in as theta. And that's our point. All we know for sure is second coordinate is -5/13. And, well, I think we pretty much put down all the information stated here. And it says, use that information to calculate sine theta and cosine theta. Turns out one of them is a freebie. Anyone spot which one you can calculate immediately? And what its value would be as well?
Did they give us the sign as -5/13?
I think I heard that right. Did you say sine -5/13?
Yes, that's what I said.
Yeah, absolutely. So just as you said, this is a second coordinate. So sine itself is that second coordinate. The moment they gave us that, they're hiding information, but that is sine theta, the second coordinate on the unit circle. Does that make sense to folks on this one here? Okay, so here's our next task. We need to get cosine theta next. But to do that, we can just use that Pythagorean identity. T can have been any angle or theta or any variable you'd like to throw in here. So let's start next by saying cosine squared of t plus sine squared of t equals 1. So we brought in our Pythagorean identity. And this Pythagorean identity is nice in the sense that we're defining 6 trigonometric functions. If you have information on just one function, you can evaluate every single other one just based off knowing the value for cosine or knowing the value for sine. Every other function is now determined. And this is the identity that helps us, so let's work it through. I have a feeling we might need more space, so let's drop this to the next page as well. First thing we need to do is, like Michael was mentioning, we have to be extremely careful with order of operations. When you see things like cosine squared, sine squared, we're going to input this inside of sine squared, but here's the way it actually looks. Cosine squared of t plus power of 2 goes like this. Input the value for sine, -5/13, and then it gets squared. T, nothing happens to that. T is not being doubled, it's not being squared. It's always just right here. Sine squared t just says square the output in essence. So definitely new and interesting notation for trigonometry. Does it make sense to folks so far, right here? Okay, at this stage, we're just going to simplify this out and get an answer. I don't think this one is very nice for an exam setting. If this was a real exam problem, I try to make my numbers a lot more easy to work with, because I understand exam 1, exam 2 is closed calculator. And just for information, when I write my exams, I do solve them before I actually give them out to the class. If I see a problem like this one where the numbers aren't great, I will modify it. Let's continue. We're solving this equation for cosine squared, so we can resolve this. That's going to be the end of our work here. So on the next step, cosine squared of t, here we'll square this and get 25, 169. So cosine squared t plus 25 169 equals what? We might as well take that 1 there and call it 169 169. Because now we need to subtract 25 169 from that fraction. Upon subtraction, you get cosine squared of t equals 144 169. So that's where we land so far, but we're not quite there yet. We want cosine, and we've got cosine squared. So we need an algebraic operation to get to what we really want. Any volunteers for the next suggested step? Yeah.
You just
Exactly. You can
square root
square sides. Yes, absolutely. So like folks said in class in Zoom, square root both sides. But the moment you square root both sides, we have another conundrum. There are two possible answers that we're going to deal with if we squared both sides. Suddenly, this information has become really, really vital for us, and just as much the negative 5/13, I'd say. But more specifically, the quadrant is really relative out of nowhere. The quadrant will tell us what sign to pull. Any volunteers for the correct sign on Zoom or in class?
minus 12 by 13. Minus.
Exactly, it's going to be negative. But the reason is, here at quadrant 1, cosine will be the first coordinate, and it lives right here. That's the cosine of that coordinate. It's definitely on the negative end of the x-axis. So we will be using the negative results right here. Let's call this square root of cosine squared is just cosine of t. Throwing in the negative, only keeping it. Square root 144 to get a 12. Square root 169 to get 13ths. And that's finally our answer. Cosine of t is now negative 12/13. And let's leave our answer like this. That's my first part of the answer, and that's my last part. I'll leave this still kind of hanging because that's how we started the question, determining what needed to be found. I don't like to always box out my answers, but if my actual end result is all over the page, it's not a bad idea, mainly just to make it more readable if you go and look at these notes again. Well, any questions at all, folks, on getting both sine and cosine?
Yeah, so like the question says theta, but like you change it into t. Should we just keep it at theta or?
Oh yeah, that should have been my mistake. That should have stayed as a theta. Not sure where t came from. Thanks for spotting that. So everywhere here, this is my mistake here. Oh, there's a lot of them. All the way through there, those should have been thetas. That was weird to change the variable all of a sudden. Let me put those corrections in. So theta here, 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 and here. It's always bad mojo to make a mistake right there and then carry it down. That could really affect your work. You could have done that as well. Yeah, if you make that kind of mistake, but go theta equals t, you have algebraically resolved that conundrum. It just makes it slightly confusing to the reader, but you are allowed to do that kind of thing. I mean, that's just demonstrating knowledge about algebra after all. Other questions or comments so far? Yeah. I'd say for those problems, you're pretty much going to see instructions that say round to 2 decimal places on those kind of problems. And those would be the kind of problems that are really just exclusively homework problems. They wouldn't be on the exam. But say I did do a weird problem and the root was weird. Oh, Control Z that though. If I did give a weird problem on an exam and you had something like root like 1/7, you're okay to just leave it just like that. Absolutely. Other questions so far? Okay, I had to Control Z something. Let me make sure it's all back. Okay, well, I think we got it, folks. This question is weird because notice what we determined. We determined a sine value, we determined a cosine value, and notice what we still don't know. I have no clue what the angle theta even is, but we can find it. What we need is an inverse function. We might take sine inverse, or we might take cosine inverse. So that's why we're not just defining functions, we're also going to define their inverses as well. But as promised, the next major thing that we need to do in this course is take a look at all these angles and determine why are we getting values like 1/2 √3/2, √2/2, √2/2, and so on, so we can start calculating with these sort of things. So that takes us to one more derivation in these notes. Because it's a derivation, it's not something I would ask you to do at all as a homework problem, but it's more we're practicing using some of the concepts we saw in these notes just to get more fluent with them, is I think the word to say there. So first thing I have on our next example, where we're going to derive sine pi over 4 cosine pi over 4, is this little chart. Sometimes this is called a chart of reference angles. Let me show you how to read it. You really just want to go row-wise. So for example, we're going to derive this, but if it said evaluate sine pi over 4 cosine pi over 4, this is how you could think of it. Cosine pi over 4, go down to the row for the angle, and it should output to √2/2, and sine pi over 4 should evaluate to √2/2 as well. So that's how we're reading the table. Likewise, for example, we already know that sine at pi over 2 is 1, cosine at pi over 2 is 0, but this row is just as interesting as well. It's saying sine at pi over 6 should be 1/2. Cosine at pi over 6 should be √3/2. So this reference angles turns out to be just enough information so that you can extrapolate from this quadrant to the entire unit circle, whether the angles are positive or negative. Everything happens pretty much right here. I want Moodle over here so I don't have a red spot right there. But let's first derive at least one of them. I want to derive the one for pi over 4, since it's not as much of a bother. But if you're curious, pi over 6, pi over 3, let me know, and I can put some notes up on the Moodle website for how those derivations go. Exactly, since that one would be sine over cosine. Well, to get this derivation, really the first thing you'd want to do is just draw the unit circle. So here it is. I do want something additional on this unit circle. Let's draw the line y equals x. We mentioned about this line, if you recall, that this line is pretty special. That what's special about y equals x is the angle it makes right here. And we recall what that angle would be. Sorry, say again. Exactly. So from here to here, pi over 4. So we have the angle in question. Now, next thing we need to do is we need the coordinates right here. We do have the answer, but we're trying to figure out how you would get that answer. So we need to now call this an x and a y coordinate. Let's drop down a perpendicular. Down here, the distance here to here is x. The distance from here to here is y. So let's take this whole thing. It's a little bit busy where it lives right now, and let's blow it up over here. So imagine we magnified it a whole bunch, and let me see if I can draw it a little bit better, actually. That should be more perpendicular looking. So here's our right angle. Now, the distance here to here is x, like we mentioned. The distance here to here is y, like we mentioned. Keep in mind, this is just a hand sketch, so the scale is not perfect at all. I think the scale is a little bit better right here. But this y is special. Everything that you see about the variables is all in the same scope. So the moment you wrote that, y equals x, and you use that actual terminal side, you can go over here and say, y is also x right here in this diagram. Both sides are equal, I just didn't draw it very well. So imagine they are perfectly equal. We still need one thing in order to get our derivation to run through. we need to know the length of that hypotenuse. So we need to know its exact length. Any volunteers for what it could be? Good call. This came from the unit circle. It's a radius. So it came from x squared plus y squared equals 1. The 1 there says every time you draw these kind of things, they are a radius of radius 1. So that's our triangle. If you think of this in terms of A, B, and C, you can use the ordinary Pythagorean theorem. A squared plus B squared equals C squared. Really, it's the same thing. It's a Pythagorean identity, but we're thinking of it relative to this right triangle this time. So let's take A, which is x, and square it. Take B, it's y, but it's also equal to x. So we're going to square x. Our C is 1, and we'll square our 1. There it is, it's squared. Well, 1 squared is just 1. The left-hand side contains like terms, so now we have 2x squares equals 1. Divide by 2, and we have x squared equals 1/2. We gave it a little bit of space because we're going to use that same idea, solve for x by square rooting both sides. And although it's not as big of an issue this time, it's considered good practice to at least think these thoughts here. It could either be positive or negative. It just depends on the quadrant. But here we're off in quadrant 1. The x position is this value. It's a positive quantity. So we'll pick the positive sign on this one. So now we have x equals positive. Throw in that sign just to emphasize we chose that one. We'll take the square root of 1 for the numerator. It's just 1. Square root of 2 doesn't reduce, so we'll leave it like that. So there it is, folks. It's 1 over root 2. Seems suspicious, right? Now, some calculators, some computer systems, they'll use 1 over root 2. But in a lot of textbooks, they rationalize the denominator on us, and we use root 2 over 2. That's a stylistic choice of using your numbers. And just for overall advice in this course, how should we say this? This might be better typed out. It is never required to rationalize denominators in this class. So I just want to put that there as an overall emphasis. If you decide to use 1 over root 2, you're not doing anything wrong. But the reason why I'm going to really rationalize the denominators is it's so common that if you're ever checking, say, the back of the book for the odd exercise answers, you might get stumped if you didn't rationalize your denominator because your work looks different. So I'll commonly rationalize just for that extra practice and being able to compare answers in the back of the book if you're doing that. So we have the right value of x. Rationalizing the denominator means we're multiplying by root 2 over root 2. Across the numerator, it's 1 times root 2, so just root 2. Across the denominator, we get 2 altogether. And that's finally where all this stuff comes from. Instruction said derive sine pi over 4, cosine pi over 4. Let's make that our end step. So we can say here, therefore, let me choose a different color. Therefore, cosine at the input of pi over 4, which is x, but x was found to be root 2 over 2. Likewise, sine in pi over 4. Well, that's always the second coordinate y. We never want to forget that, but this was a special diagram at that 45-degree line where y is x, and it's back to root 2 over 2. So that's a kind of an interesting angle, pi over 4. At pi over 4, because y equals x, sine and cosine output the same exact result, root 2 over 2. And that was our derivation. The one for pi over 6, pi over 3, it's the same kind of idea, but they're different ideas. It took a little bit more algebra, so I felt like this would be the better one to derive. Any questions or comments at the moment? Okay, so what we just did with that derivation there was we found that at pi over 4, sine, or let me point to the right thing, sine is root 2 over 2, and cosine is root 2 over 2. And pi over 4, just to help orient where it is the 45-degree angle. So this diagram is tremendous But for the purpose of this course, we have to memorize these values ourselves. And the most important thing to memorize is not everything here. You really just want to memorize this, just the radian measurement particularly. And the reason for that is, if you've got those angles down, the reference angles are going to tell you everything else about the outputs. You just have to know what quadrant did it land in. If the denominator was pi over 6, it'll either be a positive 1/2 or a negative 1/2, depending on whether it's a 5 pi over 6, 11 pi over 6, and so on. Well, that takes us down to example 4, evaluating the following using reference angles. I suppose we could finish this today, but I think what I want to do is, let's do the problems that are here right now. And when we come back on Tuesday, I want to revisit these notes again, just do a couple additional problems before we segue to 5.3. So I'll practice a few more off this section on Tuesday's class. Any questions at the moment? Okay. Well, it says evaluate the following using reference angles. Let's just say this again because we're back up here. Here are those reference angles. And these are some tricky looking angles, like say sine pi over 4, but here's how we would get started. Sine at pi over 4 is either positive root 2 or it's negative root 2 over 2, and we have to figure out which one it is. But you can find that out by just doing this. Here's your unit circle once again, and I would just count out the pi over 4s. Here's pi over 4. Up here is 2 pi over 4 or pi over 2. These go by odds. Here's 3 pi over 4. This would be 4 pi over 4, reducing to pi. And I'll stop right here because this one's 5 pi over 4. If the question was evaluate sine at 7 pi over 4, I would have put the 7 pi over 4 over here. But I typically wouldn't rotate that far, just as far as I needed to go. And if you have good knowledge and memorization on this, you maybe practice it a bit, you might have only drawn this much. You would have said, well, 5 pi over 4 is here. That's what I'm going to work with to get our values out. Now, looking at this again, if you did have the reference angles, let's hide them for just a bit. Here's another thought. Go right here. Sine is going to be which one? Is that the vertical or the second coordinate, or is it the horizontal or first coordinate? Exactly. We're going to go to the vertical value. And it's that value right there, whatever it is. There's a couple values that are pretty typical here. There's, say, -1. There's going to be negative root 3 over 2, which is about 0.9-ish if we're rounding really roughly. Negative root 2 over 2 is about, oh, that's a negative 0.7-ish, and so on. And so when I see this, that looks like a negative root 2 over 2 to me, just by the diagram. It's not even a very good diagram. So what I would say is, it's certainly negative. We landed on this quadrant where sine takes on a negative value. The reference angle says it should be negative root 2 over 2. But we probably suspected it because we're not close to a 0.9. We're about here, around a 0.7 in the diagram. So sometimes it's pretty helpful to know that root 3 over 2, roughly a 0.9, and root 2 over 2 is roughly a 0.7, because those are not too hard to spot on here. Well, we did it, folks. That's our first evaluation using different angles, a little bit trickier ones. Any questions about that one so far? Okay, let's try this out again. Now with cosine at -5 pi over 3. Here's how I'd probably answer this thing. Cosine -5 pi over 3. We need a reference angle. But when we say reference angle, we're thinking the denominator is what gets us there. Here's the pi over 3s. We want a cosine. So my anticipation is, well, it's either positive or -1/2. And all the work is just deciding what is the sign. We have everything else right here. Well, let's put down a new unit circle diagram. And here's what you could do for reference. We're dealing with a pi over 3 this time. Oh, let me double check. Yes, we're dealing with pi over 3. And when we plot those, they go 1 pi over 3, 2 pi over 3. we come down and get 4 pi over 3, 5 pi over 3. Everything is flipped on us because the angle is negative though. So we're going to take this whole thing, flip it like that vertically.
So it's
So
just
let's
like,
count out those.
oh, sorry. So it's just gonna be like positive pi over 3 because it's flipped, it's negative.
Exactly, yes, absolutely.
Okay.
So that's kind of the idea with this altogether. All we really need to know is where does that end up? And if you're not sure, you could go like this. Here's negative pi over 3, negative 2 pi over 3. Like you were mentioning, the whole thing's flipped. So instead of going this way and this way, I rotated the other way, negative pi over 3, negative 2 pi over 3. Keep on rotating, and that always just looks weird. Let me do it that way. This is going to be negative 4 pi over 3. And just as Hayes said, this location really truly is negative 5 pi over 3, but it happened to be just the same as the location of pi over 3 this time. Let's take a look at what we're going after. We're dealing with a cosine, so we project down. Cosine is on the x-axis. And even if we were looking at the reference angles, you know what that looks like to me? 1/2. It looks like it's pretty close to dead on 1/2. Take a look at the reference angle. It in fact is. Now it's positive 1/2, and that was the whole thing we had to resolve with this. What is the sine? Well, any questions, folks, with this approach at the moment? Okay, so again, the reference angles are wonderful. If you look throughout this unit circle with the outputs here, you'll notice that the 0, the 1/2, root 2 over 2, root 3 over 2, they just keep repeating over and over again, whether I'm looking at the first coordinate or the second coordinate. So if you know these values for pi over 6 through pi over 2, including 0, and you know where your angles terminate, whether you're rotating in the positive or negative direction, you have pretty much everything. Let's emphasize with this as our very last question. But first, any comments at the moment? Okay, we're doing a 7 pi over 6. Let's work this one out. It's our last problem for the day, so we might as well make a big unit circle. We're going by pi's over 6. Now, you could start right over here. Here's pi. It's the same as 6 pi over 6. But this one is 7 pi over 6. So we rotate 30 degrees further over to here. Now, here's 7 pi over 6. So that's where we want to be, matching the angle. Because we're dealing with sine, the output is going to be on the y-axis. So just go directly to the y-axis. And you could, if you have memorization of the chart above, just say the value. But when you do these drawings, even if your circle isn't a perfect circle, you can almost guess what it should be. It'll look like a 0.9 or a 0.7 or a 1/2. I'm saying 1/2 here, but I did make a mistake. That's a negative 1/2, right? Let's put in the negative sign. Negative 1/2. So back to 7 pi over 6, all we have to say is this evaluates to negative 1/2. And that's the idea of doing the trigonometric evaluations. The reference angles are really pretty powerful because every time you see a pi over 6 and you're dealing with sine, that 1/2 will keep on coming up. All we're deciding is what quadrant did we terminate. So if we have to change the sign, we can make that change. But that also means for the purposes of exams, we should be very familiar with this table right here. We need to memorize where all of these angles end up to help us out. And the negative sign is actually pretty important. If this was, say, a 3-point question, I would give the negative sign 1 point out of the 3 because that is a big takeaway for this particular problem. But we'll practice a few more of these when we come back from the weekend. And before we call it a day, any last questions or comments, folks? Okay, so 5.1, we define the domain. In 5.2, we define sine and cosine. And in 5.3, we'll define everything else, tangent, and then the reciprocal functions. But for the moment, the only thing that's considered fully assigned is going to be assignment number 1. We're going to do a couple more problems here, and we'll push the due date on this assignment number 2 as well when we come back after the weekend. But have a great night, folks.
Thank
If you
you.
do have questions, be happy to help out. Otherwise, have a good one. And thanks for all the participation in class, especially over Zoom. I think it's hard to participate over Zoom sometimes. So I appreciate your folks making that happen. Thanks, Jamie.
Thanks.
Chris again. So really cool. These are the Maclaurin series for sine and cosine. And you define these in calculus too, if you're going for that subject. And doing more work with those kinds of functions, you could put a complex number inside there. Yeah. Yeah, that infinity summation is really kind of punishing there, but when you put, say, in your calculator, cosine of 0.3, it's using either the Maclaurin series or Taylor series, and it's just deciding how many terms do we need for 8 points accuracy. What was that, sorry? Awesome. Yeah.
So it's hard to turn in the end, you just wants to either, you can either write it or like, I just put it on
Yeah, that would work out great as
stuff
well.
and then.
Yeah, that'd be perfect. Then I'll mark it up like your normal math class, nothing over Zoom and such, and hand it right back to you.
Okay, perfect, yeah, I already basically did it, but I wasn't sure on this one, I was like, I don't know which way he wants it, so.
Oh, gotcha, yeah. Cool.
Thank you.
Yep, you betcha. I think sum is a good term, good way to say it. How many terms you'd have to sum up? You know, there's a cool thing you could do. You could go to, yeah, let's go to Desmos. Well, let's see if we can still get it going. Let's try the one for cosine is an even function, so I think that one's easier. So here's cosine x. And for cosine, the Taylor series for cosine should be something like, let's see, y equals. Yeah, I think I need to take a look at that. Maclaurin for cosine. Okay, the Maclaurin series for cosine goes, geez, 1x squared. Okay, so we've got the pattern down. Let's put it in 1 minus and then plus. So in Desmos, you'll go 1. Horrible approximation, but we're approximating next to 0. So we're trying to get, say, cosine 0. Then go minus, so it'll be x squared over 2 factorial. Then it's going to be plus x4, 4 factorial. And the more terms you add, the more you're going to get accuracy. And it's also going to expand out to the right, out to the left. It's actually kind of remarkable. So your question of how many terms do you need? It's going to depend on how much accuracy you want and how far away you are from 0 as well. But you could recenter this. This is the Maclaurin series because it's centered at 0. You could center it at 5 if you need to do cosine 5. Suddenly get way more accuracy out of that. Was that what you were asking about, how many terms for accuracy? Turns out, if you're approximating around here, 3 terms is fantastic already. Kind of weird. Well, have a good one.